Okay, so sorry about the previous one. My recording time was over. So, well, it's just then that's actually it's really just a matter of writing the remaining stuff. So we have trace of A2 transpose B, and trace of lambda times the matrix is lambda times the trace. Again, if you really are not sure about that, you just have to write what it means. Take the trace, check the sum of the linear coefficients, multiply the matrix by value lambda, you multiply the whole sum by the same value lambda. Okay, right, so that's it, it's linear, and then positive definite, so that's interesting. That's something you should try again. Okay, so for positive definite, what do we get when we take the trace of A transpose times A? First, it can be interesting to see what is going to be, sorry, A transpose times A, the matrix, the product of those two matrices. So according to what we already said, that would be the A transposed IK, so 4K is equal to 1 to n. So the coefficient ij of that matrix product is going to be given by this times A times kj. So now if I take the elements on the diagonal, that would be A transposed ik, aki on k, but the A transposed ij is of course the ji coefficient of the non-transposed matrix. So this would be exactly the sum on k of A ki square, right? So of course I've got positive definiteness very directly. That's just going to be the sum on k equals 1 to n, the sum on I equals 1 to n of aki square. Okay, so sorry, I should have written it in the first the sum on I and then the sum on k, but well, actually it's not going to change anything. The thing is that what we are doing is we are describing the sum of the squares of all the coefficients of the matrix A, and so that means first of all it's always positive, are equal to 0, and it's equal to 0, it means that again I've got a sum of non-negative terms equal to 0, so all of them have to be equal to 0. aki squared is equal to 0 for all k for all I, so that implies that aki is equal to 0 for all k for all I, and so that A is the 0 matrix of size n times n. Okay, so 0, that's not the notation. So these are also, it's more or less the same kind of proofs. Again, the hardest part is usually the positive definiteness part. I can advise you to try some more examples. Now, what if we define E to be the space of continuous functions on some interval I, such that so with real values, such that the square, the integral of the square is bounded. Okay, do we have that this definition is also a well-defined inner product? Okay, so that's interesting. You should try that example. It's very there's a lot of things that are similar to what we wrote earlier, but yeah, try this one. Another example, another ID. What about a space of sequences? Um, and you can also make those complete exercises by first proving that those spaces that I'm talking about are linear spaces, and then prove that we have a well-defined inner product. All right, so another example, let's consider a space of infinite sequences and such that sum of the UN square converges. Okay, infinite sequences such that if I take the series of the squares, it converges. Do we have that if I define something like this? Okay, I'm defining a product of these two sequences as the infinite series of un times vn. Is that a well-defined inner product? Again, so an interesting exercise. We can do, well, there are a lot of exercises like this, and maybe these are good exercises to try for you.